Thanks everybody for joining the discussion. We're really excited to talk about radar cross-section with you today and all of the exciting developments that are wrapped around our whole simulation platform. So looking at the registrant list, there's quite a broad range of skill types and industry and job titles that are represented. So we'd like to give a quick overview of what radar cross-section is, just so we can sort of level set everybody. We're a simulation company. We're certainly going to be talking about how to simulate radar cross-section and why we can trust these results, and we do that with test comparisons and benchmarks. We're going to be talking about the different simulation types involved in a radar cross-section analysis. So we'll go over full wave techniques as well as shooting and bouncing ray techniques, which we're really excited to introduce to you today. And we're certainly going to spend time talking about the fully integrated workflow that we get with our electronics desktop platform. And you're going to be seeing lots of applications that are kind of dispersed throughout the presentation in the form of monostatic and bistatic. We're extremely excited to talk about our radar post-processing as well, and that comes in the forms of range profiles and inverse synthetic aperture radar that we're really excited to focus on at the end of the presentation today. So let's just get right into it. A quick overview of radar cross-section. Radar cross-section can be thought of as an inherent property of any target that's illuminated by a radar. It's a quantitative way to define how reflective an object is with respect to that incoming radar wavefront and return signal. So energy is typically reflected or scattered in all directions, but RCS is measured in just a predetermined few. The units, it's convenient to think of radar cross-section in units of meter squared or dB squared meter, dBSM, which is decibel squared meters. Radar cross-section is commonly referenced to a perfectly smooth sphere of 1 meter square projected area. There are other ways to reference a RCS measurement as well. It's convenient to think of the equivalent sphere size that would produce the same response if it were placed instead of the true target. So mathematically, this is one way to define radar cross-section. So sigma represents the RCS value. You can see there's a scale factor in there, and there's a numerator that is defining the scattered power density. And in the denominator, we have the incident power density. So we can think about a radar cross-section in terms of this ratio of the backscattered energy that's normalized by the incoming energy. And of course, in a radar system, not all of the energy is actually impinging on the object. So we're usually focused on the energy that actually illuminates that object. So we'll be talking about monostatic and bistatic. So we use both of these terms when describing radar cross-section. In both of these terms, the target is illuminated from a single angle of incidence or a look angle, with the difference really being in the location of the receiving radar. So in a monostatic radar, the transmit and receive antenna are co-located, whereas a bistatic analysis, the transmit and receive antennas are not necessarily co-located. So we can break down radar cross-section into these broad categories with respect to the applications. So we can think of traditional applications as well as emerging applications. So let's start with the traditional applications. So target identification is probably the earliest application for radar cross-section. Here's an example where we've got a land-based radar that's used to characterize a number of seagoing vessels near the coast. And as you can see, the type of vessel that's indicated here, depending on its size, could be measured in tens of meters squared for RCS, if you're talking about something like an inshore fishing vessel, or thousands of meters squared if you're talking about something like a tanker ship. And it's worth noting that there's quite a range of values if you look at the minimum and max values, and that's because the response that you get from an illuminated target is really going to be dependent on that look angle, which can vary quite a bit depending on the orientation of the object and the radar itself. Another application that falls in the traditional sense is certainly radar signature reduction. So vehicles designed to elude radar detection use RCS as a key figure of merit in design. So by evaluating radar cross-section across multiple illumination angles, the geometries and the materials can be manipulated to achieve that desired result. Emerging applications can be broadly characterized as machine vision. So whether it's autonomous automobiles or flying drones, robust target identification is something that's extremely critical in this application space. So this is especially true for certifying the safety of the system. So if we think of a robust detect and avoid system for UAVs, it's critical to ensure the safety as the airspace grows crowded. So RCS provides an important metric for target identification that helps flesh out the complex real-world scenarios that need to be addressed. Along similar lines, advanced driver assistance systems, or ADAS, require a comprehensive awareness of the surroundings. So this includes the ability to understand threats such as abrupt lane changes or braking from adjacent vehicles, and distinguish them from some of the benign roadside features that could include things like parked cars or guardrails or buildings, or also pedestrians in some complex dynamic scenes. So RCS really provides a huge opportunity to create an extensive database of features and to test the intelligence of these control systems that are actually being developed. So finally, in the category of situational awareness, that involves a large space where radar imaging can really add to the intelligence of decision-making systems. So here's just one example that we pulled from a publication on remote sensing, where synthetic aperture radar satellites are being proposed as a way to develop global traffic monitoring systems. And in this application, the RCS of passenger cars is really indispensable in applying this type of monitoring technology. So how do we acquire RCS data? So testing is still a very important part of the process for characterizing or certifying RCS. The downside, of course, is really in the area of cost. For those of you who are fortunate enough to have a facility that you can test in, you're aware of the extreme effort it takes to certainly make a chamber and keep the chamber quiet. There's maintenance involved in ensuring that the RCS measurement is not unintentionally picking up effects from the chamber itself. The test equipment is very comprehensive. It's a very complex, tool chain that includes signal generators and positioners and combiners and collimators. And just conducting the test itself can be extremely time intensive. For the most part, testing RCS of vehicles is something that's typically measured in days or weeks. And this is where simulation really comes in. So the business case for simulating is really nothing new. It's been done for decades, especially with RCS. And the idea really is just to create this virtual test bed that really liberates you from the constraints of the physical world. So there's no restriction in the number of measurement points. If we change our mind on the types of points we want to observe, then it's very easily done by reconfiguring a simulation and rerunning, and there's really no need to reproduce the test. The same goes for reconfigurability studies, where we want to understand maybe feature characteristics. So with an analysis, you have the ability to hot swap CAD models in a simulation without having to generate the actual physical prototype of interest for all these different test points. And that goes the same for material properties. So you can just as easily set up parametric analyses where you can look at the impact of different material coatings, where some of these materials might be transparent at some frequencies and opaque at others. It's very easy to just reconfigure a simulation model along those lines so that sort of behavior can be understood. And then for dynamic scenes, you can really get a feel for the sensitivities involving these complex scenarios that would just be extremely costly to be able to conduct on a pure test basis. So here's an example of an RCS characterization that's just enormous in scale. So at 10 gigahertz, the aircraft carrier shown here is about 10,000 wavelengths in electrical dimensions. So this simulation actually includes the seawater. So the complex interactions with the vessel and the ocean surface are included. So even if the certification is required by test, the simulation really provides a reliable tool to iron out the important conditions of interest before the test plan even gets put into motion. So why should we believe in the simulation? The best way to prove that is to make comparisons to theoretical values and to test programs. So for reasons already mentioned, we don't have access to chambers of our own, but there's certainly plenty of available literature. So we just chose 3 publicly available data sources that we use to compare our Ansys simulation tools with these theoretical predictions or test data. So for the most part, what you're going to see are going to be comparisons for the monostatic case. And they're typically done where a look angle is decided on, so we have a certain theta or a phi, and then we'll sweep in the other direction. And typically these are copole cases, which means that the polarity of the emanating wavefront is going to be aligned in a particular plane, and it's going to be received in that same plane. And that's where the terms VV and HH show up. It just implies a copole condition for one of the preferred planes. So the first thing we do for a comparison is actually take references from the handbook. And in this case, these are theoretical predictions that are made for a number of canonical targets. And the values that are calculated are all analytical, and the term that we're looking for is actual maximum radar cross-section. So for the objects that you see here, the sphere, cylinder, plate, and corner reflector, we can punch in our own values and get a theoretical estimate for what the maximum radar cross-section would be. And then we run that simulation in our Ansys HFSS solvers. So here we see the results over various cut planes for the monostatic RCS of the trihedral, the cylinder, the plate, and the sphere, going left to right, respectively. And you can see up on top of the plot, we do a direct comparison between the theoretical value and the maximum value that we get from our simulation result. And as you can see, by comparing these numbers, the Ansys simulation agrees to within a fraction of a dB. So now we move on to actual test comparisons. This is a result for the metallic ogive from reference 2, and you can see the geometry in the middle of the slide there. At 9 gigahertz, the object is less than 10 wavelengths in all dimensions. But you can see for both the HH and the VV polarities, we get excellent agreement when compared to measurement data. We get very similar comparison when we looked at this so-called NASA almond. It's a kind of a similar shape, about the same electrical size here. And at 7 gigahertz, we're looking at HH and VV polarities, and you can see we get really, really good agreement here. And then finally, for reference 3, we chose the metallic prism. You can see the electrical size for 2 different frequencies that we called out, for 8 gigahertz and for 10 gigahertz. And you can see really excellent agreement in the VV polarity. So we'd like to move on and spend a little time talking about the solvers themselves. We're not going to go through any mathematical derivations, but we would like to talk about the solvers in the sense of how to use them in applications. So HFSS has certainly evolved significantly over the years. And what really started as a finite element solver for problems of pretty modest size has grown into a tool of enormous reach, and that's particularly true in the area of radar cross-section targets. And this is really done by the additional techniques that have come into HFSS over the last few releases. And what you're going to be seeing today is really focused on the addition of moment methods techniques, which are also called integral equations. And what we're really excited about is the shooting and bouncing ray technology, which we refer to as SBR+. So in an application sense, it's really convenient to think about these three techniques in terms of model complexity and electrical size. So for objects that are very complex in geometry and materials, HFSS FEM is the gold standard and has been proven in a wide array of applications. And as we move to objects that are larger in size, we can switch to the integral equation technique at really no cost and accuracy. And the advantage of doing this really shows up in improved simulation speed and lower hardware overhead. And furthermore, you can link these two techniques in a single model, project, or interface so that the most efficient technique is actually leveraged. So we can continue this progression to include enormous objects that are hundreds or tens of thousands of wavelengths in size by switching to shooting and bouncing rays, and an even more dramatic speed up and hardware efficiency is actually realized. And the philosophy behind all of this is that we don't just throw a bunch of solvers at you, rather we give you an integrated platform that links solvers to the parts of the models where they belong, and the whole process is fully interactive and intuitive, and it all takes place in one interface. So we'll spend a little time talking about this SBR+ methodology, and in order to do that, we have to introduce traditional shooting and bouncing rays. So it's an asymptotic technique, and asymptotic techniques are complementary to full wave solvers, and particularly in the fact that they apply to electrically large platforms. So usually when you're comparing to a full wave technique, an asymptotic technique is going to take over when the electrical size of that problem starts to get dominated by features that are multiple wavelengths in size. Shooting and bouncing rays extends physical optics to multi-bounce with geometrical optics ray tracing. So it's physical optics essentially at its core. It allows for material modeling, and that comes in the form of dielectric or magnetic stacks or Fresnel table imports. So SBR+ takes that capability and adds onto it with additional physics that are coded into it. And those physics come in the form of improved diffraction handling. So we allow for physical theory of diffraction at edge corrections. We also allow for uniform theory of diffraction edge rays that allows for a different type of diffraction handling, especially in the area where secondary structure in the shadow zone could be important. And we also do creeping wave for certain problems. And the objective of all this is to use the full array of GTD and UTD methods to paint currents on the scattering geometry body and then radiate those currents to field observation points. And all of these mechanisms work together to improve the accuracy. So the name of the game is to really paint as many currents as possible that are handled responsibly, and the accuracy of that solution improves significantly. So why not use SBR+ all the time? And the answer is because it really comes with handling conditions. So when deciding between using asymptotics in general and full wave techniques, you really have to ask yourself two questions. The first question is, are the dominant physics mechanisms properly represented in the asymptotic solver? And the second question is, does the model meet that electrically large criteria? And there's a really good example that sort of demonstrates both of these points just by considering a metallic sphere that's illuminated by a plane wave. And if you look at the image in the bottom left corner, it's the exact same model that shows surface currents that are produced in a full wave version of that simulation and a physical optics version of that simulation. And you'll notice that in the lit region, the distribution of those currents looks very similar, but it's pretty noticeable that with just pure physical optics, we really don't account for the energy and the attached currents that are showing up in that shadow zone. And that's an example of the fact that a full wave technique really handles all of those physics for free. But in a physical optics solution, that has to be coded in to be able to match. And if you're looking at pure physical optics, you simply don't represent the physics the same way you do in a full wave solution. The other question about electrical size is kind of demonstrated, or at least exhibited, with the plot that you see on the right-hand side. So in this example, you're looking at a normalized radar cross-section. So the vertical axis represents the RCS value. The horizontal axis represents the electrical size. So on the left-hand side, you've got geometry that's, or specifically the sphere, that's electrically small, so it's sub-wavelength. But on the far right side, it's electrically large. So you're talking about an object that's about 10 wavelengths in size. And the full wave solution, highlighted in red, agrees with what we get with the theoretical prediction. And there's lots of literature on this. And what you notice right out of the chute is the physical optics solution is just flat out wrong at the electrically small end. And it's not until you get into electrically larger conditions where they start to converge. And that's expected. And these two results are really just a reminder that there's certainly engineering judgment that needs to be applied when using asymptotic techniques. But as we're about to find out, when you use them correctly, it really opens up the space for what we can do. So let's go back to some of the canonical test objects to put these different techniques to the test, and we can talk about some of the performance benefits that we can get. So we start with the model on the left-hand side, which is a finite element solution, where we applied a perfectly matched layer boundary condition. And in this example, it was run on a fairly modest workstation that had 20 cores and over 100 gigabytes of RAM, which was all needed to solve this problem in a few hours. Now, if you compare that solution to the integral equation solution, the IE solve was about 40 times faster and takes about half the RAM. And if we continue that and compare that to the SBR Plus solution, we get down to a solution that takes on the order of 12 seconds on a laptop computer with RAM that's practically negligible, 45 megabytes. And if you look at the comparison, the first thing you notice is that it's a very large dynamic range problem. You're talking about 80 dB of dynamic range for both copol results. The red and the blue traces represent the FEM and IE results, respectively. So they're practically on top of each other, which is really no surprise. Again, these are full wave techniques. It's the most accurate representation, and all the physics comes in this for free. But you also notice really good agreement with the SBR Plus result, in particular in the upper half. So almost all of the features above negative 20 dBSM are tracked. And even in the low return region, the majority of those features agree. And considering the time improvement going from multiple hours of a solution to just seconds, this is extremely good agreement. Another example is with our cylinder. You can see the electrical dimensions called out, same frequency. If we look at the IE solution, it takes about 1 hour on a laptop of about 10 gigabytes of RAM. And the SBR Plus solution is taking about 48 seconds with 40 megabytes of RAM. And the agreement for both VV and HH polarities is extremely good. And then we look at the prism result. In this example, we've got the IE solution down to about 8 minutes, but the SPR Plus solution is down to just 13 seconds. And if you compare these results for the 8 and 10 gigahertz VV, we're also comparing to test data in this case. You can see that the results are excellent. And finally, we'd like to end on an example with geometry that has dielectric loss. So in this example, we've got a target that's a simple metallic rod, and it's about 6 wavelengths long with lossy dielectric layers applied. So at theta equals 90 degrees, the long side of that cylinder is illuminated, and you see perfect agreement with the theoretical prediction. It's not until we move theta down to about 180 degrees where we start to see the disagreement. And that makes sense because we're illuminating this object from the bottom side, which means the only features that are seen are the electrically small spherical end caps. Those are sub-wavelength, and we already know that SPR Plus is not the appropriate solution for that type of problem. So it makes sense that we get disagreement down at that look angle. So this is a really excellent agreement for treatment of dielectric materials. All right, so we'd like to take a little time and kind of step through some of these, the advantages of some of these advanced physics mechanisms that are built into our SPR Plus. So if we start with just shooting and bouncing rays, reminder that that accounts for multiple reflections. So if we think of an incident wave as being discretized in a number of ray tubes that are ultimately carrying off that energy, those ray tubes are going to interact with some scattering geometry. And when they do, they deposit currents. And those surface currents are going to be radiated into free space. And the result is obtained by combining the effect of every one of those deposited currents, no matter where they end up. So with traditional shooting and bouncing rays, not only does the first bounce show up, but that current from the second bounce is also going to get deposited in the third. And that's indicated by the different color of rays that you see here that will interact inside this trihedral and then finally get lost in space. Now, physical theory of diffraction correction actually improves those painted currents in the vicinity of the sharp edges. So if you think of the deposited current, it's non-uniform when it shows up near one of these abrupt edges. So the currents typically are decreasing in one direction and increasing in the other direction, which is very unlike currents that might be deposited in the center of a large section that might be far from these edges. So adding that PTD correction makes a significant improvement on the result. And then we can think of the UTD rays that are used. And in this case, the UTD ray can be thought of as additional rays that are generated at those same wedges that the PTD correction is made. But in this case, these additional rays are basically propagating diffracted energy along the so-called Keller cones. So if there's structure that's behind one of these wedges, UTD rays enables it to propagate and deposit additional current in secondary structure that might be in a shadow zone that would otherwise have no way of being represented without this capability. So it tends to really drive the number of rays that are in a solution, but it can also make a huge impact on the accuracy of the solution. So if we can just look at a comparison here, we go back to our metallic prism. And if we run the SPR simulation without PTD correction on, we can see that we get really good agreement up at the peaks, but there's lots of room for improvement down at the nulls. So when we add PTD correction to this problem, it's dramatically cleaned up. And we can see those nulls are really back in agreement as well. So now we'd like to switch gears and go from some of the benchmarks and look at maybe some more practical targets that you might be experiencing. So we'll start with this example of a quadcopter that was solved at 10 gigahertz. So you can see it's about 36 wavelengths in size. And this is an interesting model because it's very practical and it's complicated as real life is by all of these mixed electrical sizes. So at some look angles, the platform is electrically large, and SPR is giving a really accurate result to the full wave result. But at other look angles, it's really dominated by electrically small features that we know SPR is going to have a difficult time with. And one of the things that we like to say about an analysis like this is that if you are going for the most accurate solution, and that's all you want, then you're probably going to stick with the full wave simulation here. But even though we can see some of the discrepancies, the SPR plus solution gives really good correlation across the suite. And it gets into a business case where it only takes 5 minutes to run an SPR simulation. It really enables you to go through some of the multiple configurations where maybe you're getting some directional information, knowing that you can always come back and then hit it with the big hammer. That's going to be the full wave simulation that improves and guarantees your most accurate result. So it's really a situation where it's able to provide guidance in this early design and scenario stage, knowing that you can always clean up and get an accurate solution with full wave techniques. As we move up in electrical size, the disparity between the integral equation solution and the SPR plus solution really starts to diminish. And this is a good example of that. At 1 gigahertz, it's not a really super high frequency, but the object itself, this passenger aircraft, is 200 wavelengths or more at that frequency. So this comparison shows really, really good agreement, as most of those features are electrically large, and you're kind of getting out of the issue of the mixed electrical size. And again, you compare the SPR plus solution, that's 400 times or more faster than the full wave solution, and it's only taking about 1 gigabyte of RAM. Now, we already talked about the aircraft carrier, but in this example, we've got another geometry that's extremely large. So, you finally get to the point where it's just impractical to use full wave techniques. And if you've got an example like this, the International Space Station at 10 gigahertz, it's something that's over 3,000 wavelengths in size, and it's really dominated by all of these large features, which means that, as we've seen, SPR plus is going to give us a very accurate result. So now these things that just could not be solved before are done using SPR. So up until now, we've really been focused on monostatic or bistatic RCS. And as it turns out, there's a lot more information to be obtained. And this is really where range profiles and inverse synthetic aperture radar imaging comes in. So at very little cost, additional cost, we can augment the settings of a monostatic or bistatic analysis to obtain these results. So for example, if we add a frequency sweep to a standard monostatic RCS, we can get a range profile that allows us to pick out features that are distributed along the object look angle. So additionally, if we add not only frequency sweep, but a look angle sweep, we can start to get enough information to reconstruct the entire radar image. So as you'll see, this is extremely powerful data that can augment monostatic and bistatic RCS. So a range profile is really focused on identifying features at some distance from a predetermined target center. And the way it works is you can think of our radar requirements that ultimately generate our simulation settings. So for radar requirements, the first thing we need to know is the downrange extent. So that's the distance to the target. It's the range. So we can call that X max. And another thing we need is to know what the downrange resolution requirement is going to be. So think of what's the minimum distance between discernible features that you're interested in. It could be centimeters or it could be meters, whatever. It's a value that basically, along with the range extents, we're able to use to determine what the appropriate frequency sweep is going to be. So given just those two values for our radar requirements, we can define what the bandwidth our simulation is going to take. And we can define the start and the stop frequency, the number of steps, and the distance and the separation between those frequencies. So those are really the only things we need for the simulation settings. And once that's done, we ultimately get the same thing that we would get with a network analyzer and measurement. And then we can take that and apply an inverse Fourier transform to be able to get the result that we're looking for the range profile. So let's run through a couple of examples here. So in each of these following examples, the simulation settings are going to be shown up on top of the plot. So in this case, we've got these collections of spheres. We ran the simulation at 5 gigahertz, and we defined a downrange resolution of 0.1 meter with that bandwidth that's indicated there over 71 steps. So the vertical axis in this case is giving us the response of the backscattered power, and the horizontal axis shows the range to the object. So notice in the middle of the horizontal axis, we've got a range 0. So that corresponds to the target range defined previously by that X-max value. So think of a negative value on that as features that are in front of that target range, and positive numbers correspond to features that are behind that target range. So here we're comparing range profiles from full wave and SBR plus techniques. So you can see the SBR plus in red and integral equation was used in this example in blue. And it's worth noting that even with these electrically small targets, these spheres are basically, three wavelengths or less. You get really good agreement in that all of the critical features are really agreeing here. So if we change the geometry to the flat plates of slightly larger size, in this example, these plates are about 6 wavelengths. You'll notice for the exact same settings, the agreement gets a little bit better, as you'd expect. You're practically getting overlay in this case. So all these critical features are agreeing because the electrical size of these objects has grown, and we know that SBR plus is going to give us a better result in this case. And now here's a practical example that exhibits features of mixed electrical size. So we're talking about a geometry for this generic missile that's 64 wavelengths at 5 gigahertz. And this is really a fantastic comparison that shows agreement of most of the major features, even though some of the components are sub-wavelength. The fins are just 1/3 wavelength in size. And just remember, at 64 wavelengths, SBR plus is given a really useful result in just a fraction of the time compared to what we get with a full wave solution. So here's another practical example of a really large, a physically large target that's illuminated by an automotive radar system. So at 77 gigahertz, this target is 4,000 wavelengths long, so it's really large. The scene actually includes the interaction with the asphalt road surface in this case. And you can clearly identify the major features, and you can gain insight into some of the secondary things that are happening with the interactions of multipath that are taking place between the asphalt surface and the undercarriage and substructure of the trailer there. So it really gives an interesting and valuable tool to be able to understand some of those complex features that might not be very intuitive. We can also use something called a waterfall plot to extend range profiles over multiple look angles. And this really helps correlate object features with illumination angles. So if you look at the image on the right, this is very similar to what we were just looking at with the semi-truck. And you can see all the major features for a given aspect angle are identified, the nose of the aircraft, the engines, and the tail. The image on the left basically takes that range profile from all 360-degree cuts and stacks them on top of each other as a color map. So the vertical axis now is showing a combined 360 degrees of look angles, and as a color indicator now, we can see how those features are interacting and how they're sort of coming in and out of dominance depending on the aspect angle. So it can really be a powerful way to get additional insight than just multiple or single range profiles. Okay, so an ISAR image is focused on not only identifying features that are down or up range, but also to the left and right. We call that cross range. So the radar requirements actually become an image size requirement, and this defines the sweep angles and the steps in addition to the range settings previously discussed. So if we just kind of revisit our radar requirements here, we're already familiar with what we need for a range profile. That's X max and delta X. Now we have the cross range requirements, which is Y max and delta Y. That corresponds to simulation settings that, again, the range profile settings are there, but now we also see this additional aspect angle. So it's really akin to just providing a range profile for a given look angle and holding on to that range profile with additional look angles and using all of those results and providing the Fourier transform to generate that ISAR image. And if we look at the same examples that we were looking at with range profiles here, we can go back to the configurations of the sphere, and you can see the simulation settings that are called out on the bottom. All the same numbers there from the range profile, except you'll see the addition of this aspect angle at 17 degrees over 51 steps. And that gives us that cross-range resolution we need to generate the map that you're looking at. So again, even with electrically small targets, again, these spheres are three wavelengths and 1.5 wavelengths in size. You're getting really good agreement from the SBR generated image on the left compared to the full wave image, which is shown on the right. We go back to the plate example, and it certainly comes into a little bit more focus here. We get really good agreements with the plate. And then what's probably of most interest are the practical models that, again, this is one that had mixed electrical features in there. And if you look at the comparison between the SBR image on the left and the full wave image on the right, it's pretty hard to tell the difference with resolving those features and identifying those features. And as a reminder, at 64 wavelengths in size, that SBR plus result is extremely fast compared to what it takes to run the full wave solution. So I'm going to end on this example that I think really epitomizes the value of using simulation and being able to run what-if scenarios and really just diagnose real scenes. So this is our semi-truck that we're familiar with from previous slides. In scenario 1, we see the ISAR image that we can clearly identify some of these major features. Now, in scenario 2, we open the trailer door, and all of a sudden we see a number of these additional features that pop up. And if you do a close inspection on what those features are, they're basically corresponding or they're correlated to geometric features inside the trailer. So in particular, these vertical supports are really showing up as corner reflectors, which we know are really good targets for an RCS analysis. And you can even see the relative strength of the far corner, which is much larger than those smaller vertical supports that show up. So what's also interesting is that there's a number of these ghost images that show up. And anybody who's familiar with doing radar processing of complex scenes is going to be confronted with these ghost images. So these are features that are actually artifacts of the multipath inside the trailer, and they're accurately handled by the simulation here. So, you know, you really have a way to look at diagnosis of some of these ghost images and help develop and test a robust detection system where you can properly flag things that might be viewed as false targets. And one final point is if you look at that small image in the top right, you can actually see, using our visual ray trace tool as a way to further diagnose something just based on pure geometrical optics, try to figure out where some of that multipath might be coming from. It's a really convenient way to do that. So we expect the audience members are certainly going to be a lot more creative than we can with the types of things that you want to analyze, but ISAR imagery certainly is a really powerful technique to be able to make sense of extremely complex scenes and help develop and prototype some of the, automated systems that are in development. So if you weren't taking notes on all of those analysis requirements that we just put in for range profiles and ISAR imagery, don't worry, we've done all that work for you, and we've done it in the forms of what we call Ansys Customization Toolkit. So this works for our SBR solver as well as our full wave solvers. So let's say that you've got a monostatic problem in mind. You can just pull up the pre-processing form and define the range, the resolution, the frequency, and polarization that you want. And when you hit the go button, that analysis model is going to be set up for you and ready to go. And once you have a solved result, you can now pull up the post-processing routine. And again, you can define your cross-range resolution, your down-range resolution, the ISAR imagery size. You can define what you need for waterfall plots. You can choose from a dozen or so built-in windowing functions and actually customize it to put your own windowing functions in if you want. It's extremely easy to use and to set up. So all this is available for you now. And as a reminder, it's not just the radar post-processing or pre-processing that we try to make easy for you. It's really the entire workflow. So Electronics Desktop is a single interface that allows for several different design types and applications even well beyond RCS. So if you were to open up a blank project in Electronics Desktop, you'll see that the different solver types are available for you all within one interface, and even different disciplines are represented in this interface, including things like circuit simulation or low frequency. So it's really integrated and intuitive. Electronics Desktop also supports, practically all types of CAD formats. So we don't just limit you to Ansys CAD. If you want to work with CATIA models or SolidWorks models, or if you've got a neutral format from a customer, everything is supported. So you're allowed to import that directly into the interface without any need for manipulation in some third-party tool or any other tools. It all works directly inside Electronics Desktop. And it doesn't matter if it's a NURBS-based geometry or if it's faceted geometry. We accept all kinds. Another thing that's important is HPC setup resource control is available all directly inside the interface. So whether it's controlling multi-cores, let's say on a laptop on one computer, or maybe distributing a job across a multi-blade Linux cluster, you can just set up a configuration one time and then call that configuration with however you want to distribute your job. So this goes with multiple cores as well as multiple cores working in conjunction with GPU. So we've got simulations, especially with the SBR solver, that are seeing a boost in speed of over 100 times. So we're really efficient at the way that we utilize and allow for setup of HPC. We also have the ability to set up parametric and optimization runs all within the same exact interface. So if you decide that you want to make some components parametric, maybe it's an orientation or maybe it's a material parameter, you can define that variable directly inside the interface. Once that variable is available, you can go to our parametric form and set up a sweep. So it's really not dependent on on geometry, so you could go through material properties, anything you want, and you can run batch results of these, and you can also perform optimization on it. So it's all available just inside the same interface. And configuring a simulation job is extremely easy and interactive. So if you want to change solver types, you simply hit the appropriate button in the form and click on the geometry that you want to apply a particular solver or region to. Some of the things that we saw with setting up of these advanced physics runs with the SBR Plus solver, wedge extraction is an automated process, so it's extremely easy to just enable wedges and let the interface itself hunt down the wedges for you without you having to go interactively find them. And again, we get to choose from a number of really comprehensive report types. They're all available, again, in the same interface. So whether you've got 2D cuts or tables, or you want to look at full 3D color maps, you can create as many as you want. You can export data to process with whatever tools you want. It's all available there. So if you want to post-process in MATLAB or anything, all these results are available to you just from our direct reports. So in summary, Ansys Electronics Desktop provides a platform for very accurate prediction of radar cross-section for a wide array of targets. I hope that you've seen that SBR Plus can really extend the reach of radar-related simulation to targets that are just enormous in size.